Hi, I'm Rodrigo Dowd, and in this video I'll be presenting Guided Depth Super Resolution by Deep Anisotropic Diffusion. First, let's review the problem setting. For Guided Depth Super Resolution, it starts with a scene that is observed with an RGB sensor. This sensor produces a high-resolution RGB image and an aligned lower-resolution depth map of the scene. What we want is to combine these two images to obtain a high-resolution depth image. We propose a novel method which computes diffusion weights from the guide image and then solves a test time optimization comprised of a diffusion step and an adjustment step. This results in transferring edge details to the output while adhering to the source constraint. The result is a guided and constrained diffusion whose steady-state solution contains edges defined by the diffusion weights and therefore by the guide, while also sticking to the constraint provided by the source image. The diffusion and adjustment steps work in tandem to transfer details from the guide into the optimized result, which is constrained by and initialized using the source. There are three main parts to our method: computing the diffusion coefficients, performing a diffusion step, and performing an adjustment step. Let's start with the computation of the diffusion coefficients. From the high-resolution guide, we want to assign weights to the horizontal and vertical edges of the connectivity graph given by the four neighborhoods of all pixels. In its simplest learning-free formulation, this can be done directly using the guide's RGB values. This can also be done using learned features, as we will discuss later. A monotonically decreasing activation function, C, on the magnitude of the difference between adjacent pixels is used to obtain diffusion coefficients bound between 0 and 1. These coefficients should have low values at discontinuities and high values close to 1 inside continuous surfaces. Once these diffusion coefficients are computed and given an initialization, we can compute the next image at t+1 using a discretized version of the heat equation. This formulation allows us to transfer edge details from the guide onto our final result. As we perform more diffusion iterations, the edge discontinuities defined by the diffusion coefficients become more visible in the output. Nevertheless, this is not enough to ensure that the output is indeed a super result version of the source image, since the diffusion will relocate energy inside the image. To ensure that the result adheres to the source, we need an additional adjustment step in the test time optimization loop. We start with the diffused image y hat t and the source s. We can then downsample y hat t to compare it to the source. This gives us a scaling factor RT, which can be applied patchwise to correct y hat t in such a way that it guarantees that if subsampled again, it will match the source exactly. Here we have the full schematic of our method. Note that for the supervised version, a feature extractor F processes the guide and the upsampled source to obtain feature maps from which the diffusion coefficients can be computed. Please refer to our paper for the exact implementation details that make this possible. In our formulation, we are able to backpropagate through over 1,000 iterations of the diffusion process to train the feature extractor end-to-end. The advantages of using learned features becomes clear in surfaces which are flat but contain color gradients. In this image, we see a flat surface with color textures as well as a depth discontinuity with weak color gradients. In the supervised RGB version, the diffusion coefficients are confounded by the background textures and fail to place a sharp edge in some of the depth discontinuities. In the supervised version, the feature extractor learns to map the pixels in such a way that the resulting diffusion coefficients are more adequate in these regions. We observe accurate transfer of details from the guide to the final result during the optimization. The diffusion over time is displayed here as a video, where we can see the evolution during the test time optimization. We also go beyond previous work and super resolve with a factor of 32 while still observing good results. This shows the strong generalization that is enabled by the inductive biases of our method. We observe good performance across a wide variety of scenes. We consistently see that edges are transferred accurately from the guide image to the optimized result. The constraint diffusion clearly allows the optimized result to follow both the source constraint and the edges defined by the diffusion weights. We have quantitatively compared our method to several others in the literature. The unsupervised version of our method, represented by the red line, outperforms all competing methods at a variety of upsampling scales. We also compared the supervised version of our method to competing approaches. Once again, we observe that our method outperforms all other approaches. The superiority of our result is especially pronounced for larger upsampling factors, such as times 32. Similar results have been observed using 3 well-known datasets in this field: Middlebury, NYUV2, and Dimmel. Our paper and the provided supplementary material contain in-depth analysis of how our method performs under different conditions. We analyze the required memory for training and applying our method and compare it to the requirements of LGR, a recently proposed and very powerful method for performing guided depth super-resolution. We also study how the number of diffusion iterations used for training and inference affects the results and the computational requirements. Code for our method and pre-trained models have been made publicly available. For more details on this work, please refer to the main paper, the code, or contact the authors. Thank you for your attention.